So let's explore calculating equilibrium information given partial information in the problem. That is, partial concentrations, maybe an equilibrium constant, perhaps not. And in this case, what we need to solve for are unknown concentration in many instances given partial information about those concentrations. Sometimes what we're going to calculate is the equilibrium constant itself. So two pieces of information are needed. We need a balanced chemical reaction. We can't work these problems without that. And then from the balanced chemical equation, we can get an equilibrium constant expression. Or alternatively, you could get a balanced chemical equation from an equilibrium constant expression. We take these two pieces of information and we link them together in what we call an ICE table. So remember the acronym ICE, which stands for initial concentration, the change that takes place during the reaction, and then the equilibrium concentration. So the initial, that is going to be the initial concentration of whatever our products and reactants are. And the equilibrium concentration, that's concentration as well, generally in molarity, could be in pressures if we're doing a gas phase reaction. The change is actually going to be the change in X, and that's going to be reflective of the coefficients from the balanced chemical reaction. Let me show you what I mean. ICE tables. ICE tables allow us to calculate the relative changes in concentration due to a chemical reaction algebraically. So we're essentially going to be doing algebra. All you have to do is develop the algebraic equation based on this partial information. So in the example that I've got here, we begin with a 2 molar concentration of reactant A. And so we denote that right here as 2 molar. That is our initial concentration. So that's all we've got so far. So we're starting out with only a concentration of a reactant A, which means that we don't have any of our products. So their concentration at the beginning of the reaction is 0 in both cases. Now, the change is going to correspond to whatever the coefficients are in the reaction. And the variable that we use for that change that we're going to solve for, you might guess in algebra, the most famous variable of all is X. And so the disappearance of reactant A is going to be minus 3X, 3 from the coefficient, X for the unknown change that's going to occur. All right, and then since the coefficient of product B is 1, this is just going to be plus X because reactants disappear and products appear. And I'm betting that you can guess what the change in the product C is. Since the coefficient is 2, it's going to be plus 2X. Good job. All right, then all you do is you add the initial concentration to the change in each case. So initial concentration to the change. When you add those up, you get 2 minus 3X, and then 0 plus X is just X, and 0 plus 2X is 2X. So here is where we develop our algebraic expression from the equilibrium constant expressions. We use that and the equilibrium constant expression to come up with an algebraic equation. So we have the initial concentration 2, the 0 concentration for both products, and then minus 3X plus X plus 2X, and then we simply add the initial line to the change to get the equilibrium concentration. Okay, it's just a sum of the initial plus the change to get, in each case, the equilibrium concentrations. All right, now we're going to take that and we're going to plug it in to the equilibrium constant expression. which is simply, once again, products over reactants. And then we have to employ what we've learned about raising the particular product to its coefficient as an exponent. Same thing for the reactant. So we get this expression. Then what we do is for B, we substitute x. For C squared, we substitute 2x. For A, we substitute 2.0 minus 3x, and we come up with this expression. Yes, we square the 2x because that is the representation of the equilibrium concentration of product C. All right, yes, we cube 2 minus 3x because 2 minus 3x is the representation mathematically of the concentration of reactant A at equilibrium. Now, this would be a particularly ugly math problem, so we're going to find ways to simplify. I'm going to show you how to do that. Okay, so let's start off with this problem. Calculating equilibrium constants given incomplete information. So here we've got 0.4 moles per liter, that's just 4 molar of dinitrogen tetroxide. It's allowed to react. So we're going to put that concentration here as the initial concentration of the dinitrogen tetroxide. We don't have any of our product nitrogen dioxide, so that's 0. What's our change here? Well, the coefficient is 1, so our change is simply going to be minus x. And then for the product nitrogen dioxide, that's going to be 0 plus 2x because of the coefficient 2. Now, the thing that we've learned is that nitrogen dioxide at equilibrium has a concentration of 0.525 moles per liter, or 0.525 molar. And it's asking what is the equilibrium constant at this temperature. And the reason we include temperature is because you know that the rate constants change with temperature. That means the equilibrium constant changes with temperature. All right, and we'll get into that at a later time when we talk about a thing called Le Chatelier's principle and we deal with endothermic versus exothermic reactions. Yes, it can get more complicated than this. All right, so first of all, let's solve this problem. So I've already said that we've got 0.400 molar concentration. This is our initial concentration, this is our change, and this is our equilibrium concentration. Over here we start out with 0. Then we plug in our change. Our coefficient is 1, so this is simply going to be minus x. Our coefficient for our product nitrogen dioxide is 2, so this will be plus 2x. And then we simply add up the initial plus the change, which is going to be 0.400 minus x at equilibrium. This is going to be our equilibrium concentration. 0 plus 2x, but they've given us the equilibrium concentration, which is a gift, 0.525 molar. Now, all I need to do to solve this is I need to figure out what x is. So for nitrogen dioxide, what I have is initial is 0 plus 2x is equal to 0.525 molar. So all I need to do to solve for x is, since this is 0, is just divide both sides by 2. That's going to give me x, which is the change, and that's simply going to be 0.2625 molar. I'll carry an extra sig fig till we get to the end so that I don't have a rounding error. Now that I know what x is in this particular case, I can go ahead and solve for the concentration of N2O4, because for the concentration of N2O4 at equilibrium, it's going to be 0.400 minus 0.2625. And when I do that, I get 0.1375 molar. So I already know the concentration of nitrogen dioxide at equilibrium. It's 0.525 molar. That was given in the problem. So I can simply solve for K now, which was what was asked for in the problem, remembering this is going to be NO2 to the second power divided by N2O4. And so all I have to do is plug my values in. This will be 5.525 molar squared divided by 0.1375. And I wind up with, 2. Okay, so that winds up being my equilibrium constant for this particular problem. So we will be asking you these questions, just filling out an ICE table based on the given starting conditions. We'll ask you this in class. You have an initial concentration of 1 molar for your reactant A, an initial concentration of 1 molar for product B, but your product C concentration is 0. Now let me just tell you that if you don't have one of your products, if you don't have a positive concentration for one of your products, your reaction has to go to the right. There is no other way for it to go, because in order to get to equilibrium, it has to produce product C. So the reaction will be going in this direction, in the forward direction. That means reactants disappear and products appear. And then you just add the changes together. So we will take, so for question 1, we just want to know what the change is for question 1 only. And it'll be one of these 5 answers. And question 2. So there's 5 questions in this one slide. All right, let's leave it at that.